Hey, my name's Karan. I'm an engineer on the Maps team, and I work on the core routing engine, and I work on the map matching engine. And today I'm going to talk about map matching. So over the course of this talk, I will introduce the problem of map matching. I will try to explain why we need a map matching system, and then we'll conclude with how we solve map matching using a hidden Markov model. Before we talk about map matching, I want to talk a little bit about some fundamental concepts that I will keep referring to over the course of this talk. So the first thing I want to talk about is how we actually represent the physical road network. So on the screen, I have a picture of the roads around 1455 Market Street, which is Uber's headquarters. And the way our software system represents this, this network of roads is using a graph. So essentially, you can think of it as every intersection becomes a vertex in this graph, and then every street between two intersections becomes an edge in this graph. Obviously, this is a very simplified explanation of what's happening because we also have to account for things like one-way streets and other information about roads. For example, how many lanes a particular street has. But at a high level, you can just think of it as a graph with edges and vertices. The next important concept I want to talk about is there are two types of distance computations that I want to talk about. So let's say that I'm trying to find the distance between point A and point B using two different ways to compute distance. The first distance I'm going to talk about is called the Great Circle distance, or Haversine distance. And that's simply the shortest path distance between 2 points on the sphere of the Earth. When I say shortest path, I mean that you're literally traveling along the curvature of the Earth. So you're not allowed to bore through the Earth's surface or anything crazy like that. So that's called Great Circle distance, also referred to as Haversine distance. So I'll use the terms interchangeably. The other distance I want to talk about is called shortest path distance. And this is the distance computed by any classical routing algorithm like Dijkstra's or A*. And it basically follows the topology and the geometry of the graph. So you basically have to obey the rules of the road, and you have to traverse along valid edges and legal edges. And there's a lot of literature about finding shortest paths in directed graphs that you can read upon. But let's just say that in this picture, I've used Dijkstra's algorithm, and this is the shortest path between A and B following the edges on the graph. So if you really think about it, the Haversine distance kind of sets the lower bound for any algorithm that needs to find a shortest path between 2 points on the surface of the Earth. Like, nothing can be better than Haversine distance. Like, if you find something better, that means you have a teleportation device, and then none of our routing software is going to work for you. But I don't like to think about that. Anyway, let's talk about map matching. So what is map matching? Well, map matching is the problem of taking in raw GPS signals, which in this picture are the red dots, and basically mapping it or matching it to road segments that those GPS signals actually correspond to. Like Arabjit mentioned, like GPS signals that we get from phones have no notion of being on a particular street. So they're kind of like close to the streets, but not exactly on it. But for accurate positioning, we need really good latitude and longitude, and we need these latitude longitudes to be present on actual physical streets in the world. So map matching is this process of taking in this raw GPS and producing latitude longitudes that are present on an actual street in the network. So the output of map matching would be the blue points shown in the picture, and you can see that all of them are actually on a physical road in the road network in the world. So this is just recapturing that. So map matching is taking in as input raw GPS signals and producing as output positions on an actual road network. So let's break down the input a little bit more. When I say we take in raw GPS signals, what we are really talking about is basically raw latitudes and longitudes that is reported by the phones, along with speed, which is how fast the vehicle is traveling, and also the direction that the vehicle is traveling, which is called the course of the vehicle. The output of a map matching system is positions on a road. And again, if we break that down, what I mean by position on a road is we produce a latitude and longitude, but a crucial difference between the latitude and longitude that we take in as input and the latitude and longitude that we produce as output is that you can be guaranteed that our output is actually present along a physical road on the planet Earth. We also produce some metadata like the road segment ID, which we use to debug issues that our map matching system might be having, also the name of the road. We also produce a direction/heading of the vehicle. And this is different from the device heading that we get because over the course of computing the optimal set of road segments, we also compute the correct device heading and we produce that as output. So when you open the app and you see the cars moving around with the direction, that is produced by map matching and then using the map match responses direction to show you the direction in which the car is moving. So why do we need a map matching system? Why can't we just use raw GPS signals that we're getting? Well, it turns out GPS signals that we get are actually pretty noisy and they can also be sparse. And in the next slide, I will show you a picture of what I mean by noisy and sparse. So let's look at this trip. So this is a trip from, I think, 2 weeks ago, which has particularly bad GPS. So the two squares at the bottom right and the top left give an example of noisy GPS. So you can see like we have a bunch of GPS points all emanating within like a very small geographical region. And this tends to happen when the vehicles are not moving or when a vehicle is in what we call an urban canyon. So you can think of an urban canyon as basically being a street that's flanked by high-rise buildings on both sides. And what happened in this case is that the GPS data that we get is obfuscated by the buildings, and that leads to really bad GPS data coming into our systems. And my colleague Danny is going to talk a little bit more about this in his talk after mine. The other problem is that we can sometimes get sparse GPS data. So if you look at the square that's towards the center or the bottom of the screen, you'll see that there are 3 GPS signals in what seems to be a very long or large physical distance. So we need to deal with these two problems. To deal with these two problems, we need to build a software system that can produce accurate location output given really bad, noisy, sparse GPS input. At Uber, we use map matching for 2 main use cases. The first one is what I term as online map matching, where we're constantly predicting or not predicting, but we're constantly taking in the driver positions when they're online and ready to accept a trip or when they're on a trip. And we're producing accurate positioning information that's used by other systems to make accurate or better dispatch decisions. The second big use case for map matching is what I term the offline use case. And it's not really offline because it still happens in one single RPC. I've termed it offline because it happens at the end of the trip where we'll take in all the raw GPS data corresponding to your trip, feed it into our map matching system, and then we get back a response, which is the map matched result for your entire trip. And then this is further used by the fare computation system to decide how much you have to pay Uber for your trip. With that in mind, let's talk a little bit about how you can actually build a system that solves map matching. So it turns out there's a lot of research that has been done in this area. I'm not going to go into details because of time constraints, but if you're interested, you should definitely read the referenced paper at the bottom of this slide. What I do want to talk a little bit about is why the simple solution where you simply take a GPS signal and decide, oh, I'm just going to match it to the street segment that's closest to this GPS signal. Like that is, in practice, that doesn't work well because of how noisy GPS data is. So if you look at this strip again, if you look at the GPS signals that I have in those 3 circles over there, if you had just simply matched it to the closest road segment, you would have ended up with incorrectly matching those road segments, and your route would have been probably impossible, which is why you need more than a single data point to give a good map matching output. And that's what a lot of the advanced algorithms like Kalman filters use. They don't operate on one point in isolation, but they take in a bunch of points and look at and make like a globally optimal decision to come out with the most optimal and most probable set of road segments corresponding to those raw GPS signals. And this is precisely what our map matching system here at Uber does. So our map matching system is based on this paper by Newson and Crum. And it uses a hidden Markov model to solve the problem of map matching. So over the next few slides, we're going to walk through a simple map matching problem, and we will attempt to build a system that can solve it using hidden Markov models. So before we do that, let's first talk about Markov chains. So what is a Markov chain? A Markov chain is a probabilistic graphical model that is used to talk about stochastic processes. The stochastic processes that we talk about using Markov chains have this very interesting property where the random variable that we're observing, also called the state, the probability of being in a particular state only depends on the previous state. So if I'm in the state S2 in this picture, I don't need to know anything else. The only thing I need to know is that what is the probability of transitioning from S1 to S2? Like, that's the only thing that being in the state S2 depends on. So if you look at this picture, you can be in the state S1 and with a 10% probability transition onto state S2, or with a 90% probability just remain in S1. That's all the information I need. Like, everything only depends on the state before mine. Another corollary, or another way to look at this, is to think of it that the probability of transitioning to a different state only depends on my current state. So my probability of transitioning to state S2 only depends on S1 and nothing else. So Markov chains are really cool when you actually can see the random variable that you're trying to predict. But it turns out in map matching, we can't do that. So we need to use another probabilistic structure, which is called a hidden Markov model. So you can think of hidden Markov models as being an extension over regular Markov models. In a hidden Markov model, the random variable that you're trying to observe is not directly visible. Hence, they're called hidden states, and contrast to a Markov chain where they're simply called states. If this goes back, there we go, yeah. Yes, so in a Markov chain, they're called states. In a hidden Markov model, they're called hidden states because you can't actually view the states. What you can view, though, is corresponding to each state, you as an observer have access to observations. And the probability of an observation only depends on the state that produced it. So you can think of it like there's the probability of a observation only depends on which state it came from and nothing else. And then the Markov property from Markov chain still holds. So the hidden states all respect the Markov property, and the observations all have a emission probability which corresponds to them being emitted from a particular hidden state. One thing I forgot to mention is that the probability of transitioning from one state to the other is called a transition probability, and the probability of an observation being emitted from a particular state is termed an emission probability. So with this foundational knowledge, we will now attempt to solve map matching. So let's try to solve a simple map matching problem where we have 5 GPS signals as input. So O1, O2, O3, O4, O5 is our input. And we want to find the most likely sequence of road segments that produced these 5 GPS signals as the observations. So let's say in our small universe, we only have 3 road segments, R1, R2, and R3. You can think of R1 as going towards the north, R2 as going towards the east, and R3 is also going towards the north. So how do we do this? How do we solve, with just this data, how can we solve this problem using hidden Markov models? Okay, so the first part of solving our problem is to figure out for every GPS observation we have, which road segment could have, in theory, produced that road segment. And we term this step as the candidate selection step. The way it works is that for every GPS signal, we do a k nearest neighbor lookup using a geospatial index. So the geospatial index can be something like an R tree or a KD tree. And then we fix k to be some number. Let's say in this example, we fix k to be 2. So we look up for every GPS signal, and we also have a minimum search radius, but I'm going to kind of ignore that part for now. For every GPS signal, we say, hey, what are the 2 closest road segments within a particular search radius? So let's look at O2. For O2, the 2 closest road segments are R1 and R2. But for O1, the only closest road segment is R1. Once we have identified these candidates for every GPS signal, the next step we need to do is we need to find a projection of that GPS signal on that road segment. So if you look at the diagram, the projection for every GPS signal is simply the perpendicular drawn from the GPS signal, and where it intersects your candidate road segment, you kind of remember that point on the road segment as your projection. So in this picture, all like the transparent black circles along the road segments would be the projections for each GPS signal. With this, we can start setting up our hidden Markov model. So all the GPS signals will be the observations in our hidden Markov model. All the candidate road segments that we picked in the previous step would be the hidden state corresponding to every GPS signal. It's important to note that one single observation can have multiple candidates, can have multiple hidden states. Because at this point, we don't know what is the most probable or most likely hidden state corresponding to one observation. We're just building up the structure for our hidden Markov model. So everything's good so far. We have observations, we have hidden states. Next, we need to compute the emission probability. So the emission probability can be thought of as the probability of seeing a particular GPS signal while the car was traversing on a road segment. For example, the emission probability corresponding to R3 and O5 would be the probability of seeing the GPS signal O5 if the car was traversing on the road segment R3. And intuitively, you would think that this probability would be higher if the GPS signal is closer to the road, and it should start decreasing the further away from the road you are. And that is precisely what is captured in this conditional probability formula on the top left of the screen, wherein the emission probability is simply a function of the great circle distance between the GPS signal and the projection of my GPS signal on that particular road segment. So we compute this emission probability for every candidate corresponding to our observations. So in this example, we'd compute, I believe it is 9 emission probabilities. The next part of the hidden Markov model map matching would be to compute the transition probability. You can think of the transition probability as being the probability of a car or vehicle traversing from one road segment to the other. So let's look at a concrete example here. So the transition probability R1, R2 would be the probability that my car traversed from the road segment R1 onto the road segment R2. And again, an intuitive way of thinking of this probability is that certain transitions or certain road transitions should be more likely than others. So which transitions are more likely? Well, any transition that involves a feasible route or a reasonable route would be a more probable transition. What do I mean by a feasible route? Well, a feasible route is defined as a route where the distance, or rather the difference between the great circle difference and the shortest path distance between the projections are almost the same. I'm going to repeat that. A feasible route is one where the difference between the shortest, or the difference between the great circle distance between the two projections and the shortest path distance between the two projections are about the same in that the difference should be pretty close to 0. And this makes sense, right? If the shortest path distance between two roads and is about the same as traversing the road graph, that means you're pretty likely to take that. Versus if to go from point A to point B, you have to like go a couple of miles out of the way. You're probably less likely to have driven that path when the two GPS signals were emitted. So this is captured by the formula on the top left. It is an exponential distribution. And you compute these transition probabilities for every pair of candidates between every consecutive observations. So in this case, we would be computing 10 transition probabilities. I think it's about 10. We'd be computing 10 transition probabilities corresponding to every pair of consecutive hidden states. Cool. So now we have a hidden Markov model where all the information is filled in. We have our observations, we have our road segments. We first computed all the emission probabilities corresponding to a GPS signal being emitted from a particular road, and we computed all the transition probabilities for a car being able to traverse from one road segment to the other. Okay, so now that we have all this, how do we actually solve the problem that we're trying to solve? We have a sequence of GPS signals, and we want to find the most probable sequence of road segments. If I write this down as a mathematical statement, it is basically given a sequence of observations, I need to find the most probable sequence of hidden states. And it turns out there is a famous algorithm for doing this called the Viterbi algorithm, which is a dynamic programming algorithm that you can run on your hidden Markov model, and it will just give you the most likely sequence of states. So when I run the Viterbi algorithm on my hidden Markov model, the output that I get would be the most likely sequence of states corresponding to that particular set of GPS signals. And if I view it on a map, we basically take the most likely road segments, and we take our projections, and we return the projections back to the person who called our matching system. And in this way, you have solved map matching using a hidden Markov model. Just a quick 2 slides about map matching at Uber. So map matching at Uber is implemented as a stateless Java service. These are our performance numbers for our online matching. So this is the real-time driver positioning when they're online and ready to accept trips, and when they're on trip. And these are our performance numbers for when we do map matching at the end of the full trip.